All right, last couple topics. Let's get through these and then let's go crush that AP exam on Tuesday. It's going to be awesome. Let's look at the ideas that are going to be in this video. It's just kind of the last things that don't really fit in any one particular category. They kind of all have to do with integrals, and except for that Euler's method thing. But we're going to look at improper integrals. We're going to look at integration methods, including partial fractions and integration by parts, Euler's method, and logistic growth. I didn't go too deep on the logistic growth, but I've got a lot of ideas. The problem, I guess, is what doesn't go as deep. So let's look at improper integrals. What that means is we're either going to be integrating out to infinity or negative infinity, or we're going to try to be integrating through a vertical asymptote or to a vertical asymptote. On the multiple choice, they like to give you questions where there's a vertical asymptote somewhere in the bounds. They like to give that to you and just expect you to just evaluate it without thinking about it. So you need to be careful. If you're given an integral that you know has a domain restriction, make sure that your bounds don't cross that domain restriction. And if they do, you need to do an improper integral to see if it converges. Basically, the idea is rewrite the integral and evaluate it as rewrite it as a limit and evaluate. I'm going to do integration by parts here because my first example requires both improper integrals and integration by parts. Basically, we use integration by parts when there's some product and a u sub doesn't work. U sub doesn't make the product go away. The thing you choose to make u is what you want to go away, usually. But if that's not something that you can logic out, then you can use that detail acronym to help you choose what dv is. So it's dv is exponential functions, then we pick trig functions, algebraic, which is polynomials, inverse trig, and log. That's what we pick for dv first. So it's just a little acronym to help you out. All right, first one, consider the function f given by f of x equals x e to the negative 2x for all x greater than or equal to 0. We want to evaluate the integral from 0 to infinity or show that the integral diverges. Okay, so just like we were looking back on that detail thing, I'm going to choose e to the negative 2x to be my dv. So first let me rewrite this. This should be the limit as b goes to infinity, 0 to b, for, that looks like a d down there, 0 to b x e to the negative 2x dx. Okay, now this integral I'm going to have to use integration by parts. I'm going to let dv is going to be e to the negative 2x dx, which makes v negative 1/2 e to the negative 2x. Just did a quick integration. And then u is going to be x, so du is going to be dx. Okay, so that means that this integral that I wrote before, this limit, is equal to the limit as b goes to infinity of uv, so negative x over 2 e to the negative 2x, evaluated from 0 to b, minus the integral from 0 to b of v du, which is going to be negative 1/2 e to the negative 2x dx. Okay, so big thing that I've noticed a lot of people tend to forget, that first thing here, that also gets the bounds. We have to have the bounds on that as well, so make sure you don't miss that. So let's go through, find the antiderivative, plug in the bounds, and see what we get. So this is negative b over 2 e to the negative 2b minus 0 minus, well, let's make this plus 1/2. Antiderivative of e to the negative 2x is negative 1/2 e to the negative 2x. Evaluated from 0 to b. And I missed that. I snuck it in there. Just make sure that you don't forget that. We got to make sure that we write the limit as b goes to infinity. You can't even see it because I wrote it so small, but make sure you don't miss that like I just did. Limit as b goes to infinity for negative b over 2 e to the negative 2b plus 1/2 let's make this minus 1/4. E to the negative 2b minus 1/2. Okay, so as b goes to infinity, this is going to go to 0. This is going to go to 0. Sorry, this should have been a 1 because I forgot I factored out that negative 1/2. So then all I'm left with is negative 1/4 times negative 1, so this is positive 1/4. Make sure this is a little clearer for you guys to see. Negative 1/4. Just this one's going to 0. So distributing that negative 1/4 to that negative 1 is how I got positive 1/4. So we had some integration by parts and some improper integrals there. There's a little bit of a cumbersome problem, but I mean, it was an FRQ question. That was redundant, free response question. All right, let f be a differentiable function such that the integral of f of x sine of x dx equals negative f of x cosine of x plus the integral 4x cubed cosine of x dx. Okay, what we're essentially charged with in this is figuring out, was f of x chosen to be u or was it chosen to be dv? Well, the integral of u dv is equal to uv minus the integral v du. Okay, so what I'm noticing right here is there's a u here and a u here. Just like there's an f of x here and an f of x here. So apparently du was chosen to be f of x. So that means du, if I look at this right here, was apparently this 4x cubed dx, which would mean that u is x to the 4th, which is our f of x. You might be wondering, well, why isn't it negative x to the 4th? Because we do see some negative signs floating around. But the only reason we see that negative sign floating around is because it's the antiderivative of sine of x. Negative cosine of x. The negative signs were going with the cosine. That's why that negative sign showed up. So x to the 4th is going to be the answer for that one. All right, let's look at partial fractions. Basically, when that's going to happen is the degree on top is smaller and a u sub or inverse trig thing isn't working. What we want to do is break it into fractions with our cover-up method, which I'll illustrate in the problem that we're about to do. And this almost exclusively leads to logarithmic answers. So if you're doing partial fractions, you're going to more than likely get some sort of log answer. I can't think of many situations where you wouldn't. Okay, so cover-up method. What we're going to do, we want to take this integral. I guess I should have mentioned that too, right? We break it into fractions by first we factor it. Luckily for us, they already factored it. What we're going to do is rewrite this integral as something over x minus 1 and plus something over x minus 5. So to figure out what goes over the x minus 1, I'm going to take its root, which would be x minus 1 equals 0. So x equals 1, that's the root of this. I'm going to cover everything else up and I'm going to plug in that 1. So I see 12 over 1 minus 5. So that's 12 over negative 4, so this is negative 3. Then I'm going to go do the same thing for the 5, for the x minus 5. Its root is 5. So everywhere else, I'm going to put in its root and simplify. So 12 over 5 minus 1 is 12 over 4, so that's 3. Okay, the antiderivative of that is going to be negative 3 ln absolute value x minus 1 plus 3 ln absolute value x minus 5 plus c. And that's this guy right here. Or girl. Our answer is gendered. Thoughts to ponder. All right, let's look at Euler's method. Euler's method is a way that we approximate function values. Basically, what it's just doing is using iterated tangent lines. The stepping up is a little awkward, a little bit like, well, which x do I plug in? I strongly believe in you. I'll let y equals f of x be the solution to the differential equation dy dx equals x minus y with initial condition f of 1 equals 3. What is the approximation for f of 2 obtained by using Euler's method with two steps of equal length starting at x equals 1? Okay, so first thing I want to do is I want to find the first tangent line. So I'm going to end up doing two steps. It even says it right there, using two steps. So step 1, we need to find the tangent line in the first place. So y minus 3 equals something times x minus 1. Well, to get the slope, I'm just going to plug in the point that I know. I'm going to plug in 1 comma 3. So that's going to be negative 2. I just plugged that into dy dx. That's how I got the slope. So to get the approximation one step away, I'm going to plug in one step away. I'm going to plug in 1.5 for x. Y minus 3 equals negative 2. Toby, don't you bark. I'm making a video. This is important. I trust you. Okay. So now I just solve for y, and that gives me an approximation of f of 1.5. So negative 2 times 0.5 is going to be negative 1. So y is equal to 2. So that's the y value I'm going to use when I make my next tangent line. BRB so I can get the dog. All right, Toby's good to go. So let's make our next tangent line. I know that the y value is going to be 2. I'm going to figure out the slope in a second. Now the x value that I plugged in previously, that's what's going to go right here. So that's going to go in for x1. My bad. So this is minus 1.5. So x minus 1.5. To get the slope, I plug in the x value, I plug in the y value. So I'm going to do 1.5 minus 2. So that's negative 0.5. Okay, now I plug in the next x value. So that's one step away. That's going to be 2. So this is y minus 2 equals negative 0.5 times 2 minus 1.5. So y minus 2 equals negative 0.5 times 0.5 is negative 1/4. Move over the 2 and you get y equals 7/4, which is C. Huzzah! Okay, I believe there's one more thing, and there is. It's logistic growth. There's really not a lot to logistic growth. It's a differential equation that you are not responsible for solving. What you are responsible for knowing are basically these 4 bullet points I have here. You need to know the form. And it's important, the way that we have identified what the carrying capacity is by making sure that that number there is a 1. So if it's not, factor it out. L is going to end up being the carrying capacity. It's going to be the horizontal asymptote, limit as x goes to infinity. All of those mean the same thing, or I guess t goes to infinity. It's where it levels off in the long run. We also know that P of t changes concavity and is growing most quickly at L over 2, so half the carrying capacity. The graph of P of t looks like an S. It looks like, kind of like that, if the initial condition is below L. And the graph of P of t looks kind of like a decreasing exponential function if the initial condition is above L. So also worth noting then is if our initial condition is above L, it will never change concavity and it will not have a growing most quickly time because it's always decreasing. So I've only got one question here. I'll do a little bit more analysis than we really need to. But the number of fish in a lake is modeled by the function p that satisfies the differential equation bleh. I recognize that looks like a logistic differential equation because there's a p here and a p here. It looks a lot like our form that we have right there. It's not in the form that we have because we would need to factor out 1,000, but it looks like it. So it either needs to look like this or like this. Well, the only one that does that is this. Only one that's an option. But like I said, I want to do a little bit more analysis just so that you can see some other things. Like I was saying, we need to factor out that 1,000. So dp dt If I factor out 1,000, I'm going to leave this as a decimal with a fraction because I really don't care what that number is. That k is just some constant. 1 minus p over 1,000. You may need to simplify numbers like this, but they're usually not quite this messy. But I mean, divide by 1,000, you just move the decimal place over 3 times to the left. So what I'm going to notice is that L is 1,000, which matches our answer choice. We've got a carrying capacity. We've got a horizontal asymptote at 1,000, which means at L over 2, I should have a change in concavity. So we should have an inflection point. And it in fact looks like we do. That's the place where it's also growing most quickly. Our initial condition we see is 100. That's how we would have recognized that it should have looked like an S between two options. But like I said, there's really not much more to it than that. That's why logistic growth tends to not come up too much, especially not in the FRQs. But these are some things that you do need to make sure you know. That's it. I've covered the pretty much everything at this point. Obviously, like I've said before a bunch of times, it's not exhaustive. It's just this is what I've seen the kind of things show up frequently on the exam. Hope this has been helpful. Please send me any questions you have. I'll be available in class, obviously. We don't have too much time left before the exam, but anything you need, let me know. I'm here for you. I want to make sure that you do well. Just let me know so that I can be there for you. Good luck, guys. Love you all.